So this talk is about the streaming engine that the execution engine we're working for Storm, for the 2.0 Storm. So currently this kind of motivation came because Storm has been around for a while. It was kind of the early horse in this streaming race, one of the early products around 2010. And ever since this, it's matured fairly well into what now the 1.x line, which is fairly stable and quite widely deployed. One of the common things we hear from the field is that it really is quite stable, works well in production, and scales well horizontally. And you've probably seen a lot of new emerging streaming products coming up fairly frequently. Maybe every once in a few months I hear maybe one more product being launched. And usually they are differentiating themselves either with features, performance, or ease of use, or so forth. Storm for 2.0, what we're doing is taking the stable, reliable system and giving it a huge performance boost. One of the things that's also being done is all of this code is pretty much now in Java, so we're moving away from closure-based code, which was there for some of the core stuff. Improving some of the back pressure and metric subsystems. Looking into adding scheduling hints and elasticity also. There's actually a long list of stuff there. I'm just kind of abbreviating that to a very short list here. So much of the stuff that I'm going to be talking about is captured in this JIRA. This is kind of the umbrella JIRA, Storm 2284. Just going to quickly go over to this and give a quick rundown of what's kind of, to give you a flavor of what's kind of in the works for, I think it's not here. You can see the at the top level, there's kind of an introductory design document sort of talking about the motivation and stuff like that. Some of the stuff that I'm going to cover here, the first one there is actually the revamp of the messaging subsystem. And we are switching from the disruptor as the messaging queue to JC tools. Then we are looking at actually a big change to the threading and execution models. Looking for supporting non-replayable sources. This kind of comes into play, for example, if you want to read data out of a source, if you don't want to necessarily push your data through Kafka and HDFS, if you want data to come in, say, directly through HTTP or sources that are not replayable. In some cases, when you're not running with hacking enabled, replaying anyway doesn't make sense. So, so that's one of the thoughts there. We are going for a much simpler back pressure model, much more efficient also. Elasticity is another thing that's being thought about. What basically this means is that the ability for your topologies to shrink or grow, based on your needs. So that also kind of comes along with the scheduling hints, because when Storm decides when it needs to expand or shrink, if it needs to know, how to multiply those or scale out those spout or bolt instances. So then we also have some thoughts around CPU pinning that, if possible, I'll try to cover towards the end of this talk if you have time. What's the next one? Batching and vectoring. What that is basically when you have batching, the general problem that comes with batching is that somebody has to figure out the right batch size, and that comes with a lot of tweaking. And then once you have batch sizes for real-time systems, you also need timeouts, which means, if the batch has not arrived, those number of elements, then you want a way to time out the batch and say, we're done, let's process as many elements as we have collected. So this, here there's an attempt to basically move away from that so that the system looks at, how many items are available in the queue and tries to pick up as many as possible rather than the user trying to optimize this, which also means you don't need to bother about batch timeouts. Once you do batching, then also it kind of opens up the possibilities of vector processing, which basically means your bolts can process like not one tuple at a time, but a bunch of them at a time. Then there's some thoughts around changing how message timeouts are dealt with. You can actually double click on, like, for example, one of these, and then you'll probably get a link there with a more detailed description about what's being kind of in the thoughts right now for that feature. What's the last one? Memory management. So memory management is a really difficult topic, especially if you're dealing with this in Java. If I have time, I'll try to give you a gist of this here. Let's see, maybe, okay. If I have the time, I'll cover it, or just ask me during the Q&A. I'll try to keep some time towards the end for Q&A. All right. So performance, much of this talk is really centered around performance. Performance is something that, if you are just given freely for whatever product you're using, you'll just take it, right? Most of you would say, why not faster? But there are some applications for whom performance comes first. They are very, very critical. Throughput, usually you can add more, if you want more throughput, you can often add more machines and get more throughput. But latency is very interesting because that's not that easy to get. Here's a simple classification, sort of a very high level of some of the critical apps, from the latency point of view, 100 milliseconds and above, 10 milliseconds to 100 milliseconds. The more critical ones is like the network thread detection. This is not just detecting a thread, but at real time, responding to a thread, because it may be too late if you wait too long to respond to a thread, if you're trying to do real-time threat responses over the network. The threat may have just come and gone. On the more very extreme end is high-frequency trading systems. This is a very, you got to be really careful when you do this in Java because of garbage collection. These guys have extreme tolerance, extreme constraints. For them, like one of the exchanges describes, a fast trading system as something that has latencies of 100 microseconds, 90% of the time, and no GC at all during trading hours. I mean, their constraints are so high, they would rather turn off a slow-running system rather than leaving it run because they're going to lose money otherwise. So, they have a lot of restrictions around GC and how often these things can occur because GC basically pauses the world for a few milliseconds. And in some of these extreme cases, these are not tolerable. So when we talk about performance, it's good to understand what do you mean by fast. So many systems, if you look around today, they will tell you they are fast. Basically, the one way to make that claim is, you compare yourself with somebody else and say you're faster than them, right? You just look around, okay, he's doing, X, I'm going to do it X plus, delta. But I think it's more interesting to look at this from the hardware side first. to see what is really what the hardware is really capable of, and then look at where you are, because that really gives you a sense of how much gap there is. So I will drill down into that, because that was the analysis I started off with when I started looking into the performance aspects for Storm. So the dimensions for performance are usually throughput, latency, and the different resource utilization. So these are the three areas kind of are, in my opinion, the most important for getting high performance stuff out of a streaming system. The first is the messaging system. Now, for a streaming system, if you really strip it down to its very, bare, what is it? It's a bunch of threads which are doing some computations, right? You have a series of computations to be performed, which are all happening on separate threads. And the intermediate results are being passed from one thread to another somehow, right? So it's a bunch of threads with inter-thread communication happening. So the logic, much of it in the threads belongs to what you do, your user logic. But what happens in the communication, the inter-thread messaging, is what the framework provides. So from the framework standpoint, this is the primary defining factor. As the faster you can move messages between threads, the faster higher your limits are of what performance you can achieve. So it's very, very critical that you use a really fast way to communicate between threads. For this, message queues are the most common option, right? Inter-thread messaging, concurrent message queues. When you start looking at these extreme performance numbers at the hardware potential, lock-based queues simply do not cut it. They are simply too slow. What you need is either lock-free queues or wait-free queues. Excuse me. So if you're not familiar with those terms, lock-free and wait-free, I'll give you a very quick idea. So these terms were invented probably in the 70s, what they mean in the concurrent programming world. In both cases, there are no locks, right? With lock-free, when there's multiple contenders for some operation, one of them will succeed, all the others will retry. When they perform that atomic operation, they realize that somebody else succeeded, and they will retry. So there's a loop there. So in lock-free, one guy succeeds. One of the contenders always succeeds. There's no deadlock ever. Wait-free, everybody succeeds. Okay, so that's the key difference. So it depends on what primitives those algorithms are using. The underlying primitives have to support them to perform in a wait-free or lock-free fashion. So we need either lock-free queues or wait-free queues, preferably wait-free. I'll talk about this a little bit later on, the message queue choices. The next major category is the threading model. Here, the basic idea is fewer threads are better because less contention. We would prefer for a streaming system to have dedicated threads rather than thread pool kind of stuff where, once the work is ready, you decide, oh, I'll send this thread to handle that work here and another thread to handle some work over there. What we would rather have is dedicated threads and data getting diverted to them. And of course, CPU pinning is another aspect of it. So the caches are kept as warm as possible. Memory model, I think I'll probably just cover this very briefly. This is actually a complicated topic. When I started looking into it, it became quite complex. But I was able to kind of turn it into two areas of kind of what you can do in the memory management space for streaming stuff. One is actually lowering the GC pressure, meaning reducing the number of times GCs run. And the way to do that is to basically try to recycle objects in the critical path. What that means is, your tuples or event objects, right? They're being generated all the time and discarded, and so maybe there's a way to, if it's possible to, I will, reuse those objects once they're consumed, and then reuse them, overwrite them with new data. But that's a really difficult thing to do unless you have started from the ground up. It's a very difficult thing to actually bring it in later into the system. And we're not really looking to break compatibility. There are a lot of, not only is it difficult to do it later on, even when you start early on, it's quite difficult because you have to start looking at, make sure you have a valid programming model where you establish where the objects are for certain no longer being referenced before they're recycled. The other one is looking into how the memory model can have a big impact on the number of CPU cache faults you have. From memory's perspective, if you have an object and with 5 data members, if they are not co-located in memory, right? If you have 5 integers in a single class and they're not co-located, they're on different cache lines. Every time you access one of the members, you have to keep taking a cache fault. That's very expensive. In languages like C++, it's pretty straightforward because they give you a co-location of objects. Even arrays, for example, when we allocate an array, you don't actually get contiguous allocation of elements because they're just references pointing to objects which could be anywhere in memory in the Java model. So actually controlling object layout is way more difficult than probably the GC, trying to reduce GC pressure, at least in the current state of affairs. The programming is quite painful. So, I just left it as, here's the problem, here's some things that are interesting, but they're really difficult to achieve unless you're willing to take on a lot of pain. So, I'll switch over to actually talking about the messaging subsystem. So, like I was saying that the messaging subsystem is actually one of the key components, right, from the framework's perspective. It governs how fast you can exchange messages between threads. So my whole perspective at the time was, let's try to identify how fast can the hardware, if I have 2 threads or 2 cores on the CPU, how fast can those 2 actually exchange messages? That's really the limiting factor from the hardware's perspective in terms of how fast messages can move. So I started benchmarking some of the lower level primitives like volatiles and atomics and lazy sets and all these kinds of things, which are the primitives that are used to build these messaging queues. And then I moved on to actually looking at the state-of-the-art messaging queues. Now here we see that here's a sort of a quick summary of some of the measurements from that experiment. So the first one there is actually Java's array DQ. It's not thread safe, so there's only one thread running there, and it's just reading and writing to the same queue, alternatively, I think. And I noticed about a billion operations, reads and writes per second. So there was only one thread operating on that queue. Then you see the blocking queue. That's actually a lock-based queue. You can see with just a single thread, suddenly the shoots down to 30 million, right? Huge, huge difference. Locks are very expensive, and actually that's without any concurrency. When you add one producer and one consumer, which are separate threads, then it falls down to 4. Giant, giant fall again. So then I looked at the disruptor queue. The disruptor queue is what we're currently using in Storm. I found about, there has a lot of different options to tweak. In particular, the wait strategy makes a lot of difference. I think the sleeping wait strategy was probably the faster one of them. And it gave me around 25 million per second. with one producer, one consumer. And usually the more producers you add, this number just drops or stays around that. So this kind of gave me the sort of, so the disruptor has this problem that, how many have you actually used disruptor queue directly? Anybody here? So the disruptor queue is actually somewhat popularized on YouTube and stuff like that as a high performance messaging queue. But it's used at the LMAX exchange, and they've done a lot of work in performance for that. But in my opinion, from the design perspective, it's probably one of the worst queues ever designed. And the reason I say is that because if I were to give you a queue, right, and ask you to use that, what would you look for in that queue? Maybe poll and basically insert and remove, right? Two methods. You will not find that in disruptor. What you will find is around 13 different concepts: sequences, barriers, ring buffers, consumers, and threading model, sleep strategies, and all these kinds of things. And it's not funny, but you can't tell whether it's the head or the tail of the list. It's really complicated. And if you want to do something slightly differently than what's actually in Manoj's example, it seems quite difficult to do. So basically, it's one queue which is trying to address way too many use cases, and consequently, it's become a really hairy beast. So I was looking for a simpler queue. I didn't find one, so I was trying to write one myself called the fast queue. The intent was to have either a wait-free or a lock-free queue. I managed to get it to about one producer, one consumer, and it was giving me about 31 million per second after about maybe 3 weeks of work on a queue, believe it or not. You need to pull off a lot of tricks to do these kinds of queues. But to take it to multi-producer, single consumer was another major effort. So fortunately, I discovered JC Tools, which had both single producer, single consumer, and multi-producer, single consumer, and all these combination different queues for each. Very simple to use. They have an insert and delete methods, and you know how to use that. And also JC Tools performed much better, right? You can see even with more producers, its performance is quite stable. It's not actually tanking really, fast with the number of producers being increased. Storm generally needs multi-producer, single consumer queue, and in some cases, it needs single producer, single consumer. So we don't really care about single producer, multi-consumer kind of stuff, or multi-producer, multi-consumer. So that's the only actual queue that I was interested in. So this kind of gives you an idea of what is the state of the art in terms of how fast you can communicate between two threads on a given chip. This actually numbers were all run on my laptop here, MacBook. Now, let's take a look at how I took a look at some of the numbers, some of the better numbers for some of the streaming systems, and sort of compared it to these numbers. Arca, which is like an actor system, which is also used in some of the streaming systems. These numbers on the right side are all taken from their own websites. I have not actually validated or done any verification. All the numbers from the left are what I have measured. So I'm just giving credit to whatever numbers they've run are actually legitimate. So in Arca, you got 50 million per second, according to them, when they used 100 threads. And they claim to be very high performance, right? If you look at the number, you should be able to get that with just 2 threads, right? Flink has about per core. They give a per core number, which sort of doesn't really register in me, because you're really thinking how fast you can have between 2 threads. But it's about 1.5 million according to their own numbers. Apex 4.3 million, Gear Pump 18 million on 4 nodes. So maybe on a single node, it's about 4 or 5 million, somewhere around that. Infosphere streams, the numbers are there, but I couldn't decode them back into, normalize them into the same numbers here in terms of messages per second within a process. I think most of the numbers are across processes. But I mean, the basic observation here is, even the fastest is not fast, right? So that gives us a clarity that we want to be able to, we can do better. We can do better, and how fast can we go? We know there's a limit out there, and we also know what the gap is. So I'll talk about the messaging architecture now. The messaging, this is kind of the current architecture. This is a very high-level view. Let me do a quick time check. So this is a high-level view, right? The worker has a receive queue, which the network data comes into the receive queue and goes into gets dispatched into the appropriate either bolt or spout, and then gets sent out through another queue on the worker. So this is all within a worker process, a Storm worker. Each of those black boxes is a thread, right? So within the spout executor or the bolt executor, you see there's two queues, a receive queue and a send queue. And the bolt, the executor logic, the user thread, the user logic is here, which is basically draining this queue. And once it produces results, it dumps it into this send queue. And then there's another system thread, which is basically just draining this queue and sending it out. So I'm going to drill deeper into this big bolt executor now. That's actually a high-level view. I'm going to give you the more detailed view of how it actually looks. So what we have here is the same receive queue, the first queue, right, the incoming queue, and the bolt executor, the user logic here, which is basically taking the data from that queue. There's this additional component here called the batcher, so there's basically one batcher per publisher. For every writer coming in, we have one batcher like this, which basically has an array list. So the publisher thread, the black thread here, with the black arrows along with it, that's basically writing directly into the current batch. Once this batch fills up, that gets drained into, that gets pushed out into this queue here. In case this queue is full, then that gets moved into this overflow queue. And every once in a while, this flusher thread comes along and drains this overflow queue into the disruptor. And the same deal happens on the outbound queue, the send queue within the executor. Basically, there's a flusher thread here and all of that sort of. The send thread is now here. So basically, right now, we have 4 threads here. So we are looking to simplify this stuff. There's a bunch of logic inside that send thread here, which basically is trying to decide whether it's to a low, when it's sending it out, is it to something local within the process, or it needs to go to a remote worker process, either on the same machine or a different machine, gets bucketed into hash maps, and then based on partitioned by the destination ID, and then gets sent to wherever it belongs. So the new architecture, what we're looking to do is simplify this. So we're going to eliminate the send queue. We're going to eliminate the overflow, and consequently, the flusher also goes, because there's no overflow, so there's no flushing required. Instead, what this becomes is when the publisher tries to write to the current batch, if it's full, right, it'll drain the batch into the disruptor. Well, but if the disruptor is full, then you can't drain this batch into the disruptor. So what happens? So then back pressure kicks in automatically. The publisher will just simply retry. So it's a very, very lightweight back pressure logic integrated into the messaging system. So this is how the new thing looks like. Basically, the receive queue getting written by the publisher, going into the executor, which then gets split into local or remote, and just goes to the destination places. So I'll give you some quick numbers here. What I observed from the early implementations is basically that in V101 of Storm, we saw around, when you have one spout emitting to a single bolt, right, we saw around 3.4 milliseconds with a latency, and with the 2.0 master, the 2.0 master numbers have been fluctuating based on when you take it, because there's a lot of development going on there. So at the time I took it, it was 7 milliseconds, but I've seen it change down to 3 and 8 and different numbers. But basically when I based this, I was based my changes on top of these. So this one is basically the new messaging subsystem. It went down to about less than 100 microseconds. So that was a dramatic improvement, right? Throughput actually was surprising numbers here. What I saw was the redesigned stuff without hacking was some improvement, 50% improvement. This looks good, but it's not really where it should be. With hacking enabled, the change was not as significant, 900K versus a million. So I started wondering what's going on there. Basically, it turned out that the messaging system was fine, but there were some additional bottlenecks, throughput bottlenecks elsewhere in the system, which were holding back the throughput. So, so latency improved dramatically, the throughput. So I kind of went chasing those bottlenecks, and these are some of the numbers I saw, because I was, you find a bottleneck by basically stubbing out a piece of code and putting some dummy code there, which is really fast, and seeing what the new numbers are. So by different, stubbing out different pieces, I noticed like numbers going all the way up to 15 million per second. And that was promising. So basically, the thing is that there are additional bottlenecks for improving the throughput that need to be addressed, and which, since as we identify them, we'll keep addressing these bottlenecks. So let me go over the threading and execution model really quickly. So here's a bolt executor. Okay, so what we're looking at doing here is allowing the change is basically to allow multiple spouts and bolts to potentially run on the same thread if the user chooses to do that. And today there is a facility in Storm which says you can run multiple bolts if they are the same type, which means they're not really communicating. But we want to flip that around and say, they better be communicating, because then there's no inter-thread communication at that point, right? It's very cheap to pass messages between them. And they have one input queue. So then, that's the grouper, which does the shuffle grouping or the fields grouping, again, basically becomes a simple task. We're going to factor it out into a task. Today, it's basically some custom code, which is glue code. We want to just turn it into just another task, just like a bolt or a spout. So basically, at the end of every executor, you'll have one grouper task, which will either do shuffle grouping or whatever. And then we also are thinking about actually, this is the code which is actually accepting incoming data from the network, which basically means it's the one which is dispatching to the right bolt, right? All the incoming traffic from the network. So that too, we are looking into factoring it into just another bolt executor, and that allows us some flexibilities, which I'll show you in a bit. So this is the incoming bolt, incoming data handler bolt. This is the outgoing stuff from the worker. So it goes to other worker processes or within the node or across nodes. Then that also means you can do some special handling for communicating between workers within a process, within a node, right? If you have two processes trying to communicate within a machine, they can probably go through a shared memory queue instead of TCP/IP, and it allows you to actually do custom things like set their parallelisms and so forth. So it's just basically a more normalized design. CPU pinning, I think I'm running out of time. I'll just leave you with the slide which basically says what the strategy is going to be. Basically run one thread per physical core, try to fit subsequent, if thread 1 is communicating with thread 2, then just put them in 2 different cores on the same chip rather than on 2 different chips, right? And and avoid hyperthreading. I'll skip memory management and some of the other slides because I think we're pretty much at the end of our times here, of the time I have. So what I'll do is I'll just take questions for the remaining, I think, two minutes. So any questions? There's a mic over there.
Why avoid hyperthreading?
Oh, so the question is why avoid hyperthreading? So the problem with hyperthreading is that, okay, what is hyperthreading? You're basically trying to run 2 threads on the same core. So if you try to run 2 threads on the same core, the first thread comes, uses the L1, L2, L3 caches to his discretion, and then when the other thread comes in, he has to refresh them all. So they keep thrashing each other's caches. So that is the primary reason for actually avoiding hyperthreading. Hyperthreading is to be used in a very, very carefully. There are very special use cases where that really gives you the extra boost. But by and large, you should be careful before you try it out.
So in the previous version of Storms, we can implement our own ACK and fail methods. But in the recent versions, it's not available. So how can we implement our own ACK and fail method? Because the counts which I see in Storm UI, it's not matching and all those things. So I wanted to implement my own.
If you're implementing a spout or a board, you can implement the spouts all have a ACK and a fail even today.
Mm-hmm. Okay, basically, then I need to look into iRich spout and all those things. I'm using basic.
I don't recall the base class, but it's not.
But one of it provides ACK and fail.
It's not gone.
Okay, thanks.
Go ahead.
So you mentioned that the JC tools queue is much faster than the Java default blocking queue. So could you explain why? Because it's lock-free or?
Well, I think it's because of the their design is just simpler. I don't know why it is, because it's very complex to go and analyze disruptor. It's a fairly fast queue. For single producer, single consumer, it gives similar performance, but multi-producer, as you saw, it was kind of dropping as the number of producers were increasing. It's very difficult to critique those designs because they are very, very complicated. It's unbelievably complicated. I learned that hard way trying to implement one of those myself. It takes, several months to get basic things straight.
But it is stable enough to use it in production, right?
Sorry?
For the JC tools.
So we will be switching to JC tools. Okay. Is that your question?
Yeah, I mean, it is stable enough to use the JC tools.
Oh yeah. JC tools has been around for quite some time. It's actually developed by the guys who built Azul system. Are you familiar? That's been tested and around for quite some time now. So it's not a new queue that's been just around. Okay, so thank you everybody and if you have additional questions, feel free to ask me outside.